Welcome everybody on Zoom. Welcome everybody in the lecture hall. Today we are going to finish, hopefully, the lecture on distributed file systems and HDFS. Before we start, I have one question to check your knowledge of last week, and then we'll go ahead. So why don't you go, as usual, to the EDU app. And this is my question to you. So you probably remember vector clocks, right? Vector clocks are the way that in DynamoDB we handle when there are inconsistencies or potentially several conflicting versions of a value associated with the same key. And the vector clock gives us some sort of clock to actually handle all of that. This is actually the context that is passed in the put function and that you get from the get function. But what is the mathematical object, the name of the mathematical object that I'm trying to tell you that without telling you the answer, to compare vector clocks. Is it a total order, a pre-order, an equivalence relation, or a partial order? Let's see your answers. We have a majority, and it turns out that the majority is correct. Congratulations. Can somebody tell me the three adjectives that qualify an order in mathematics? It's basically some sort of relation, right, over a set, but what are the three adjectives that make that relation an order? I might not actually have told you to that level of precision. Transitive, yes? I'm looking for, oh yes, here you are, yeah. Anti-symmetry, yes, and the third one? It means that X and X always compare successfully. Not symmetric. Reflexive, exactly, that's reflexive. So it's transitive, anti-symmetric, and reflexive. If you have all of that, so anti-symmetric means that if you have X smaller than Y and 1 smaller than X, it implies that X equals Y. That's anti-symmetric. Of course, that would be a non-strict version of the less than. And transitive means that if A is smaller than B and B is smaller than C, then A is smaller than C, right? So if you have a relation that takes two elements and returns true or false, basically. If it's transitive, anti-symmetric, and reflexive, that's an order. But it's not necessarily a total order, because a total order would mean that whatever two elements you pick, they always compare either X smaller than Y or Y smaller than X. But in the case of vector clocks, that doesn't work. And in fact, exactly when they do not compare, meaning that you have two vector clocks such that neither one is smaller nor the other one, right? So they cannot be compared. That's a partial order, right? So that's the difference between a total and a partial order. If you have a total order, it's like the integers. It's a straight line, basically. For an equivalence relation, the difference is that instead of being anti-symmetric, it is symmetric, right? The equivalence relation, you basically have that if X relates to Y, then Y relates to X. That's symmetric. And the other one, pre-order, this one doesn't have reflexivity. That's the difference between order and pre-order. Okay, but here I'm pushing things. I mean, this is really just to give you some mathematical foundations. So basically, the vector clocks are compared with a partial order. And for computer scientists, that would basically be a DAG, right? A directed acyclic graph. All right, so I'm done bothering you with math, and I'll come back to the slides. That was the catch box. Yeah, just put it smaller. All right. So let's continue. Yesterday, we looked into HDFS, both at the logical level. So we basically have a file hierarchy with directories and files, and every file is split into blocks. And that's it. Logically, that's pretty much what it is. Then on the physical level, we saw that we have a centralized architecture where the coordinator node is called the name node and the worker nodes, data nodes, exactly. And as you can tell with the name that they are bearing, then the data is on the data nodes, and the name node just has the metadata. So we saw what's in there. There is a namespace, which means the actual tree structure of the file hierarchy. There is a mapping from each file to the block IDs, not directly the blocks, to the block IDs, which are 64-bit integers. And then we have the mapping from the block IDs to the data nodes that they sit on. By default, 3. That's the replication level. I even showed you an animation where you write and you read, so how it's actually explained. What's the size of a block? Yes? The size of a block, yeah. Exactly, yes. So between 64 and 128 megabytes. And again, it's the order of magnitude, right? That matters. Just like, for example, when I asked yesterday, what is the maximum size of value in DynamoDB, one of you said 1 megabyte. The answer is 400 kilobytes. The order of magnitude is the same, right? So if you are in that order of magnitude, you're totally fine. And it's actually expected that the block size might change. You know, maybe in a later version, they'll make it 256 megs or 512. In Azure, as I said, they already went all the way to 4 gigabytes for the block size. Okay. I wanted to come back on the argument that I gave you, because I said the block size is picked in a way that is a good compromise to make sure that the bottleneck is the throughput. That means that 32 kilobytes, which was the wrong answer in the question I asked yesterday, does not work because you would have so many blocks that you would spend your entire time waiting because of latency, and that's not okay, right? The system would be too slow. But then the explanation that I gave for 2 terabytes, I have the feeling was a bit more fishy. And I didn't feel like the way I explained it was satisfying enough. So I would like to explain it in a different way. Why 128 megabytes rather than 2 terabytes? Basically, we try to pick the smallest possible size that doesn't have the problem that you're constantly waiting because of the latency. And that size, the sweet spot, is basically around this 64, 128 megabytes. Basically, what happens with 2 terabytes is that it would still work, but then it's almost a practical thing. You've probably already tried to upload things over the internet, over the network, right? And you notice that with very large files, there is a non-negligible probability that the upload is going to fail, right? You have a network issue or whatever, and then it stops, and then it fails, and then you have to do it all over again. Who has already been there? You know exactly. So you know the issue, right? So what do you do in that case? Well, in the case of S3, the way they do that is that they allow you to actually upload it in smaller parts and then at the end reassemble them, although it's not technically blocks, but it feels a bit like it. In the case of HDFS, the problem with 2 terabytes is pretty much that if you have a block size that would be 2 terabytes, you probably will have more failures when trying to send the blocks around between the data nodes and the client. So that's basically the reason why you want it as small as possible, so that you only need to try again for smaller blocks, right? So you basically get more efficient. And at the same time, with 128 megabytes, you don't have any latency issue because it's large enough that the system is driven by the throughput. For whom is that clear? Okay, very good. So this was it for the block size. And now, where I finished last time was that I told you there's 3 replicas by default, even though you can change it. And I told you that the way you place them is the first one on the client. So imagine that this is where you're connected via SSH. This is where your client sits. So the first block would be stored here. And the second and third one on a different rack on 2 different nodes. Now I left you with this cliffhanger. Why do we do it that way? Why don't we just put the second replica on the same rack in a different node? That would be easier, right? Or maybe more natural. Here's the thing. this is how it's done, right? So imagine, let's say that this is the client. This machine right here is the client. And I'm going to upload a file that is, let's say, 300 megabytes. So it has how many blocks? No, sorry, 200 megabytes. So it has how many blocks? 2, exactly. So it has 2 blocks. So each block will have its first replica here. So you see, you have a copy of each block, each one of the 2 blocks on the client. And then the first block will have its replicas in this rack right here in 2 nodes. And the second block will have its 2 other replicas in another rack right here, just because of randomness, right? Just pick the rack at random. So you see that here it's not too much concentrated. But let's do a third experiment and imagine that instead of that, our strategy for placing the replicas had been that we put the second replica on the same machine as the client, just like the first one. The same rack, sorry, the same rack as the first one. So this is what you get. Imagine that this is still the client, but now you place the second replica on the same rack in a different machine. So here there's only one, there could be more. But basically you see the problem here. Now everything is concentrating, or a lot of things are concentrating in the same rack. You basically have 2/3 of the blocks that are in that rack right here. And when things go wrong in a cluster, they tend to go wrong locally, right? So imagine that this rack has a problem and the network switch doesn't work anymore and so on, and the rack is down, then you basically are at risk because now you have only one replica left here and here. This is the reason. Here, you don't have the problem. Even if that rack is going down, then you still have two replicas. And even if that rack goes down, that only affects one block, right? Not all of the blocks. So you will have one copy of that one, but you still have 3 copies of the other ones. So this is why the strategy is picked in that way. For whom does that make sense? All right, and you have a question? Maybe the catch box.
Thank you. Yeah, my question was, so if for the initial copy, the issue is that we put it on, if we were to put it on the same rack, if the rack goes down, we lose those. How come having the second and third replica on some other rack doesn't make this worse? I mean, why are we not putting each replica on just a different rack altogether? Why put the 2 and 3 on the same rack?
Ah, okay, I see. Let me see if I actually come with a good argument for that. Otherwise, I'll take it offline. One argument could be simplicity, that you just keep the design simple. I think the best argument I can come up with is that when you upload the block, it's done with this replication pipeline. You remember? So it sends to the first data node, then the second, and the third. If you put 2 and 3 on the same rack, the distance is going to be small. So you're minimizing the distance of the replication pipeline. Yeah, so that would be my best arguments for that.
Thank you.
Yeah. Thank you.
So I guess maybe this is the same answer. So there's a question on chat. Why not 3 replicas on 3 racks?
Yes, that was the same question, I think. Did the answer that I just gave also answer your question on Zoom? You basically make the replication pipeline larger, and that takes more time to upload. Yes?
So it seems that part of the problem when we would be replicating on the same rack is also the fact that initially the file is sent to the same rack. Like in this case, both files were sent to like the second rack. That is also like part of the reason why there is such a large concentration on it. But if, for example, the first file was sent to the first rack and the second was sent to the second rack, then the issue would not be as apparent.
So here it's the client, the one in the middle, right? The client is in the middle, and then you have the other racks.
But couldn't there be like a load balancer that would send the request to different racks?
So the load balance has to do with the fact that different blocks pick different racks. This is where it happens. In what we're saying, there's basically 2 considerations. The first consideration is that you want to avoid a concentration of everything too much on the same rack. So that's the reason why the second block is not on the first rack. And the second thing is the minimization of the replication pipeline, which justifies putting 2 and 3 on the same rack. These are the main 2 core constraints that we have here.
Okay. Thank you.
Is it making sense or? Okay, yeah, awesome. Don't hesitate. And even, even if I don't know something, or I can still try to figure it out offline. So don't hesitate. Okay. Okay. Now I'm going to come back to something that has been bothering you yesterday, because many of you actually had brought up this problem, and actually that's a very valid problem to bring up. And the problem is that since we have this coordinator node, the name node, if it fails, we have a big problem, because that was where all the metadata was. So if you lose that, you cannot reconstruct the files anymore. You don't even know which block IDs belong to the same file. You don't know their order anymore. So you basically end up with plenty of blocks all over the place, but not knowing how to assemble them. That also means that the system is not partition tolerant, the P of the CAP theorem. It's not partition tolerant because if there is, if it's broken in two, then only the part that has the name node can continue to function, right? And not the other one. And even if it can continue to function, that would be a pretty heavy loss, because it's not just that you're losing a few data nodes, it's that you're losing many of them. So even that, you run the risk of actually completely losing a few blocks. The more blocks you have, the higher the probability that at least one block will be lost if that happens. So the system is not partition tolerance. It's available, it's consistent, but it's not partition tolerance. So it's available and consistent until you have a problem with a partition of the network. Okay, but by the way, mind that the word partition here really means the network is separated in two parts. It has nothing to do with partitions in the sense of chunks, blocks, and so on. Okay, so this is the architecture that we covered. So we have a single point of failure, and if it fails, we have a problem. So imagine, to take a simpler scenario, the name node fails, but it's not a hard crash in the sense that the server burned and it's irrecoverable. It just crashed and you just restart it. So when that happens, you lose everything that there is in there. Basically, you lose the file namespace, you lose the file to block mapping, the block location. But in order to recover, in case the computer needs to restart, you need to persist these things. You need to make sure that you recover the file namespace. You can recover the mapping from the files to the block IDs and the mapping from the block IDs to the data nodes. Question. In these three right here, one of them actually you don't need to persist. When I mean persist, I mean make a copy to the hard drive or some network attached drive. Yes? Maybe the, yeah. So your answer is correct. Say it again in the microphone.
Yeah, I wanted to say it's the third option, the locations of each block on the data nodes, because the data nodes always inform the name node about the locations. Exactly. This information actually would not be lost. You just need to ask for block reports when you restart, and you will know which data nodes have which block. So this actually you don't need to persist. So this is what you persist. So you anyway persist the namespace, and you persist the mapping from the files to the block. So all of that is stored is what's called a namespace file, right? That contains all of that information. It's a file, I'm going to be precise, it's on a network attached storage. It's basically a hard drive on the network, but not HDFS. That's very important. This is not an HDFS. This is really a standard network attached drive, and you copy over this as a file on the disk. And what happens if you made a copy of that on the disk and then the cluster lives its life, because people are editing, adding files, uploading data, deleting files, creating directories. So there is a life, right? So what you do is that you have a journal, an edit log, that just has all the changes made after the namespace file was done. So the namespace file is like a snapshot at a moment in time. And then you have an edit log that is ordered by time, right? In exactly the order in which that happens, all the events. A directory was added, a block was appended, and so on and so on. Okay, so you do that. And of course, as you continue to use the cluster, it grows and grows and grows, and the edit log is going to get bigger, but the namespace file is frozen. For extra precaution,
in addition to the network attached drive, you probably want to also put it as a backup to some longer term storage. For example, Glacier, which is the version of Amazon S3 that is very high latency but low cost, right? Can be backup drives, another shared drive, and so on and so on. So basically, not only do you want to put that on a disk, network attached storage, but also some additional backup. And then you're absolutely sure that even if you would lose the disk, and even if the name node completely crashes, with your backup, you can actually retrieve the data. The worst that can happen is just that maybe the last tiny part of the edit log could be lost if it crashed before you had a chance to put it there. But these are also things that you can mitigate. We looked into what's called the write-ahead log a bit later. All right, so let's come back to that. What if it fails? We start it up again. So what we do is that we read the namespace file from here, we repopulate the entire mapping in there, and then we play the edit log. It's like just some, you know, who knows the MIDI format in music? That's pretty much it. It's a sequencer. It's just a sequence of events of the keys you press. So it's pretty much like playing music, except that it's instead of playing music, you're playing the events. So you play the edit log and make the changes, and then you're back to the state that you had. And the block locations. So you see this is 1 and 2 here. There's the hierarchy and there is the mapping. And here the block locations, you just ask for block reports at the next start bits and recover from there. Okay, the problem is this, it's gonna take a while. For everything to restart and replay can take 30 minutes. So obviously that causes a problem because I said the system is not P, but C and A. So it's an AC system. But with A, we mean available. If we have to wait for 30 minutes, that's not really what qualifies as available, right? Or at least the number of nines in your service level agreements would not be very high. So this is a problem. And of course, that problem was addressed because we can do better than that. One easy way to do it is that whenever you see that the edit log grows and grows and grows and grows and at some point reaches some size, what you do is that you retake a snapshot at a future time and reconstruct a new namespace file that is a snapshot, but at a later time. Now you're back to an empty edit log, and then you let it evolve again. So periodic checkpoints, right, is the solution here. Okay. Next. In order to make it faster, look at the way that things are done for example, in countries in order to ensure continuity if the head of state disappears. For example, in the US, there is a vice president who takes over in every country. There is a procedure like that. Here we do it a bit in the same way. It means that we can be cautious and anticipate that the name node could crash and have some alternate name nodes somewhere else that just don't do anything, but they just wait. If in case they are needed, then they can take over. This is called a standby name node. And you can have a couple of them. You can have 1, 2, 3, you know, just a few of them. What happens is that these standby name nodes are connected to the same network attached drive that I told you about, where we have the namespace file stored in there. Again, that's not HDFS, that's really a network attached storage. So you have the namespace file and edit log. So both the active name node and the standby name nodes have access to it. And the standby name nodes basically receive the same information as the name nodes. Everything that the name node is receiving, the reports by the data nodes and so on, they are also sent to the standby data name nodes. So it means that the standby name nodes have the same memory content as the name node. They have this actual mapping in memory and the block locations and so on. They have everything in their memory at all times. So what happens now if the active name node crashes? Well, no problem. The standby name node just becomes the new name node, the new active name node. You pick one of them. And this is not going to take 30 minutes because there's everything already there in memory in order to take over. Do we have a question?
Yeah. So maintaining consistency across standby consume bandwidth. Do we face a design trade-off here?
Yes, probably. And this is probably the reason why we don't have so many standby name nodes. So you're not going to have 500 standby name nodes. You're just going to have maybe 2, 3, 4. That's typically what you do. Right? Yes?
Another question that I have is, if we now have these standby nodes, I imagine an active name node cannot concurrently handle too many requests. Can't we just also use the standby node to handle more requests?
That is a very good question, and there will be slides exactly on that. This is the dream. When you give a lecture or presentation, maybe also when you do student presentation, there is a question and you have the slides for the question. So this is wonderful. And it means your thinking is correct. You think in exactly the right mindsets, similar to the designers of the system. Yeah.
There's another question. How does the system detect an active name node failure?
Let me think about that. I guess that it would probably come from the standby name nodes that check that the active name node is still there and there is some consensus mechanism to elect a new one. I'm saying that also mentioning that usually you have additional protocols in there, like Zookeeper, that I'm really not an expert of, but there's basically additional distributed system mechanisms that basically do this sort of consensus mechanism on a lower level on that. But basically my wild guess would be that the standby name nodes are monitoring for whether they are needed to do that. But it's not like you have yet another computer whose job it is to check for the name nodes, right? That would be a distributed thing. Okay. And now I'm going, oh yes, is there another question? Yes?
So you just mentioned that the standby name node share the same information as the active name node.
Yes.
Do you mean the shared information comes from the data nodes? Like,
yes.
Okay.
Everything they send, they also send to the standby name
doesn't that mean that somehow your data node transfer time is going to be doubled?
Yes, there is a cost to that. There's always, it's computer science. Whenever you do something, there is a cost for it.
Okay.
The only exception in big data is the elasticity of the cloud, is that you get for the same price to do something in one computer in 10 hours or do it on 10 computers in 1 hour. And this is a free lunch, right? Because then you get the results after 1 hour from the same price. But this kind of free lunch is very, very rare. Usually you have to pay in some way whenever you add an improvement to the system. Yeah. Is there another question? No, maybe I thought hand raised. All right. Then I'll come back to you about your question about whether we couldn't offload some of the work to the standby name nodes. So in fact, let's start with reading. In the case of reading, the temptation was just too high, and actually that's very recent. It actually hasn't been there for a very long time. But since you have the standby name node that have all of this information, it's kind of a natural thing to ask, why wouldn't the standby name node help out the actual name node by serving reads, right? If you have clients that just want to list the contents of a directory, or they want to get the block IDs for a certain file and read it and so on, why don't you allow the clients to connect to these standby name nodes? Well, in fact, it is now possible, and this is called observer name nodes. Observer means it's read-only. So what that means is that you have the standby name nodes, you still have them, but some of these name nodes are promoted to a higher status called observer name node. And in addition to doing everything the standby name node is doing, including potentially taking over, they also can be used as alternative name nodes for read access. Right. So now you are distributed a little bit the workloads, the read workload on several observer name nodes. Of course, it's not trivial, because then you have some, you have a consistency issue that pops up. Now, how do you make sure they output the same thing? And the way that it's done, it's similar, I would say almost similar to vector clocks, but not in the sense that you would have this partial order. It's more that whenever a client is writing something to the system, they get some sort of snapshot ID or some identification of a moment in time that is the state at which they saw HDFS. And whenever a client connects to a different observer name node, they will bring this snapshot saying, this is the time I last saw the data in there. And the observer name node will make sure to be up to date, at least up to this point in time. Why? Because what you want to avoid is that a client is writing a file to HDFS, to the active name node, and then connects to another observer name node that is not quite yet up to date with that latest thing, and then the client will get the answer that the file doesn't exist. Then you have a consistency issue. You wrote a file, but it's not there. So this is why you have this little mechanism with these tokens that help you keep track of the elapse of time. But this is all linear. It's not like vector clocks with conflict resolution. It's a total order, to come back to what I was saying earlier. Okay, observer name node, is it all clear to you? All right, and this partially answers your question, right? I guess, yeah. All right, and this is the yes, go ahead.
Is update across active and observer synchronous?
Is update, sorry?
Across active and observer synchronous?
Not quite. I think this is the idea, and this is why you need the mechanism. So you might have some of the observer name nodes that are slightly behind and that didn't fully catch up. You could make it fully synchronous and so on, but then you lose on availability. It's always one of these compromises. So this is why you accept that they might be slightly behind, but you still ensure that you have some consistency with the clients with these snapshot IDs. Right. All right, you're welcome. Now comes the second part of my answer to your question, which is right here. That's called the Federated Distributed File System. It's the idea that you don't have just one active name node, you have several active name nodes. The idea is that it's just like, has anybody installed Linux from scratch? All right. Do you remember, I don't know if it's still the case today because I haven't done it in a while, but do you remember that you need to assign partitions to some parts of your file system? Right? You can say /home is somewhere and /root somewhere else, and then you have the swap and so on. So basically, it means that you have a single file hierarchy, just one, but some parts of that hierarchy might be located in different partitions on the disk. Right? This is pretty much how a federated file system works. It basically is the idea that you say, for example, /foo would be handled by the name node on the left, and /bar would be handled by the name node on the right. So of course, it can be more than two, but this is the idea. And then you just have this way of load balancing a little bit with different portions of the file hierarchy. Right, so this is my second part of your answer. Right, yes, we have a question. Maybe the catch box.
But now if the name node 1 fails and the user wants to access foo, well, he still needs to wait 30 minutes for the node to restart, right? So it's, again, not really partition of like consistent and not available all the time, what I mean. So how do we deal with that? Do we?
So is your question, just seeing if I understand, is your question, how do you combine this and this? Pretty much?
Yes.
Yeah. So I actually don't know if it's compatible. This is also something we can check. What I can say is all of that is actually work in progress, meaning that there is a regular release of HDFS every couple of months or every year or something. And every time they introduce something new. For example, observer name nodes are really recent. Standby name nodes, I think, is 2 or 3 years old now. There used to be, before that, checkpoint name nodes, backup name nodes, and secondary name nodes. I don't even mention them anymore because this is now obsolete, right? So if you see these names anywhere, then this is just earlier versions of standby name nodes. But basically, it's work in progress, and they are basically the whole idea. This is actually general in big data. The whole idea is we sacrificed a few things in order to scale. We sacrificed consistency, dealing with eventual consistency. We have the CAP theorem instead of ACID. As we will see, we don't have high-level query languages everywhere and so on. So we did a lot of sacrifice and push down some complexity and force the user to deal with physical aspects of the system. But every year that passes brings us closer to actually rebuilding the entire stack to a point that we get back these benefits of consistency and so on. So basically, it's going in the direction of making it work together. I'm sure, I don't know if they did it yet, so we will check, but even if they didn't, I'm pretty sure it's on their mind to try to also make it work all together with the federated system plus the observer and standby name nodes. Right. Does it? I think I didn't answer fully, right? But this is just to give you an idea. This is history in progress, right? This is not like mathematics where you teach something that was invented. Well, I'm not saying we keep inventing new things in mathematics as well, right? But a lot of the things that you learn is much older than computer science, right? So here, this is really the cutting edge thing. This is what's going on right now, and that's what developers are doing. And in fact, maybe some of you will actually be in projects like that and will take it to the next level, right? So this is hopefully what's going to happen. So this is why seeing that your mindset is correct, the way you approach the problem from an engineering perspective, that it matches the mindset of the developers is really good. Yes?
Yeah. So I wanted to ask that regarding the federated distributed file system, for it to work as efficiently as possible, it needs that the foo partition and the bar partition are sort of like equal in the amounts of data that they store. Like if the foo partition stores like 90 terabytes of files and the bar partition only stores 10 terabytes of files, then still the foo name node is going to suffer most of the load, or maybe, I mean, it also depends
Yes.
on the kind of read requests.
Yep.
Is this something that the system administrator has to take care of, or can it be something that's automated?
In the current state, I think it's I think it's probably some configuration that you do in the system, just like when you install Linux, right? It might be that in future version, in fact, that's the notion of data independence, right? If we extend it a bit, in an ideal system, maybe in 10 years, that would be done dynamically, that you don't even need a system administrator to figure these things out. It's just automatically distributed, right?
Yeah.
Yes, on Zoom?
Were not name nodes and data nodes actually processes, not machines? If processes, how does the path hierarchy work here?
So let me start with the first part of the question. Sorry, my voice is leaving me. Yes, these are processes. Data node is a process, name node is a process. When I speak, and actually everybody does that, you tend to call the machines name node and data node just because there's just one process on each machine, right? So this is why we abuse things a little bit and say the data node machine, the name node machine, but it's really a process running on top. So this is for the first part. The second one, I'm not sure I understand in terms of what it means with the path.
If process, how does the path hierarchy work here? So I guess it's what's assigned to one process and what's assigned to the other one.
Yes, exactly. So the process sitting on the node on the left knows that it's serving foo/foo and what's below. And the one on the right, the process running on the other machine, knows that it's serving /bar. So in terms of software, it's basically, imagine a Java jar that you just put on all machines. And then when you run the Java jar, you just pass a parameter to the jar that would be /foo on the left and /bar on the right. And then they just start with different parameters and do different things, or you do it live. Yeah. There was a question, I think I saw a raised hands over there, yes? Let me check the time too. I cannot hear you. Yeah. Okay. That is a good idea. That is yeah. Mm-hmm. Yes, absolutely. Or maybe let me do it. So the question is, why do we use the basically a path prefix in order to make the distinction between the two nodes, and why don't we just hash the paths? In fact, this is the idea in DynamoDB, right? When you hash the keys, this is very good thinking. So you should join the Hadoop team. This is exactly the right thinking. And maybe they thought about it, maybe they found reasons why it didn't work, or maybe they want to do it, who knows? Yeah, this is good thinking. Any other questions? I'm almost done, actually. We are pretty much there. Just wanted to say now on the practical side, the way you use it is that wherever you're on CSS, no, not CSS, I did too much HTML. SSH, you SSH yourself to a machine, then you can start typing this sort of commands. It's Hadoop FS, basically, and then the arguments. In fact, Hadoop FS is more powerful than just HDFS. It can also be used for your local system, for S3, for Azure, and plenty of other things, right? So this is why you could also use HDFS, ZFS, but then you can only deal with HDFS. So Hadoop FS is just the Swiss Army knife for all file systems. Okay, now here, this will be very familiar to you, I guess, because what comes next to Hadoop FS after the slash is basically the POSIX command name. So you know RM, mkdir, and all these things, right? So this is the sort of things you type to deal with files on the local file system. So this should be very intuitive to you as a computer scientist, right? ls to list, cat to display the content of a file on the screen, rm to delete a file, mkdir to create a directory, and so on. So it's very intuitive. But when you do that, you will notice one difference with the local file system. Is that when you do that on the local file system, it returns instantly. When you do that on HDFS, it might take 1 or 2 or 3 seconds, right? It's the latency. And of course, that's as expected, right? I told you HDFS is not optimized to be, zero latency. It's optimized for throughputs and large scales. And as we will see, you can have jobs that last 30 minutes, hours, and so on. So if you try it on an actual cluster, you will see that it takes 1, 2, or 3 seconds to complete every comment because of the connection to the name node and so on and so on. But if you forget about that, it feels just like a local file system, right? In fact, you even have the access control list with users and groups and authorization on read, write, and so on. Okay. You also have some special commands that don't belong to POSIX, which is to upload and download. This is very convenient when you run that from your local machine, or if you do it with the local file system of the computer you're connected to. For example, you could download from the internet with wget or curl some data set, and then you can use copy from local, with meaning the local file system to the machine you're on, and you copy it over to HDFS. What this triggers is the whole animation I showed you last week. You know, that it connects to the name node and to the data nodes with the replication pipelines and so on. But what you see on the command line feels just like the local machine. You just wait until it's uploaded, and that's it. And the other way around is to download. But of course, if you download, just make sure you have enough space. So if you have a 30 terabyte file on HDFS, then copy to local, of course, is not going to succeed, right? Okay, here I won't say much. It's just to say that you have configuration. It's done in XML. So here you can tell to this command right here, HDFS, that this is the default file system. HDFS is also a scheme with a URL. When you connect to a server, the total path of HDFS actually is a URL where you have the host, the port, and then the actual path on HDFS, and so on, right? Okay, so I won't even go into details, but just to show you that you can configure these things. Usually there's even user interfaces in browsers to do that. You don't even need to do it by editing the files. Okay, so there's some libraries like Apache Flume can be used to collect data and logging it into HDFS. Apache Scoop can be used in order to import from a relational database into HDFS to then query it with other means. Of course, it's up to you to know if that's a good idea or not, depending on your use case, right? Okay, and final concluding words. As I said, the terminology can be different. The way things are called in the Google file system might differ. What's important is not the words. What's important is that you understand what's going on. And then you can easily map the words if you change the technology. Maybe there will be new technologies. There's Colossus that was developed later at Google. So just be prepared that the words can change, but the architecture and the principles are the same. Also the block size, as I said, be flexible. The order of magnitude actually matters. All right, I'm leaving you with a few URLs. And just let me know if you followed what I've been telling you before you go. Right here. Oh, should I start it? I'm not sure actually what happens. Did we already do it, or was it from a previous time? Or maybe that's not 2 days. I was just surprised. Yeah, here you go. So thank you very much. Enjoy the exercises this week on cloud storage, and I'll see you next week at 2 p.m. on Tuesday in CAB. Thank you very much.